Dang it. This class, EGN 325, is such a pain. Then this professor gives us like, oh, a bonus. Oh, good. Well, you know what I really needed was like a chance to work for hours and hours on end for a few extra points. But they are exam points, so they are very valuable here. Here's my setup. I don't know if you guys can see that yet. I got a video camera there. I guess. Let's get started. I'm just looking at this exam a little bit here. You know, I can see that the bonus is almost the same as the exam question number 3. But then, you know, maybe I should try and work exam question number 3. I'll make sure that I work that one and see how to do root locus and what that all means with it. So if we're going to try and do some root locus work, it's good. Let's get a piece of graph paper. And I think what I'm going to do right now is I'm just going to go ahead and establish my graph coordinate axes. You know, one of the things about root locus is sometimes you don't even need all of the left half plane because these things are mostly symmetrical. They're mostly symmetrical. So here's the real axis. Here's the imaginary axis. And, you know, that I might as well, in the book, what they do a lot of is they do this. G of S is equal to, so in this one, it's 0.5 S plus 1 over S squared plus 0.5 S plus 2. So there's my transfer function, open loop transfer function, right? So if we were going to draw a block diagram, all we do is we just do it this way. This is G of S. And what we're doing now is we're going to, you know, I'm kind of putting together the closed loop block diagram, although what I'm going to do here, this is the output. And what I'm going to do here is I'm going to cut this, because I want you to remember this is the open loop system that we're talking about, even though eventually we're going to close the loop. That's what we're going to do. And so what we know about it's open loop system. So what I'm going to do is I'm going to say, okay, it starts, so where are the roots of this? R1, R2 equals 0.25 plus or minus 1.39J. All right, so we know that the open loop poles, we're going to plot those as 0.25. Let's see, how should I do this? I'll do 1, 2, 3, 4, 5. Let's call that 1. 1, 2, 3, 4, 5. 2. 2, 3, 4, 5, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Minus 5. Just to put some context on here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay. Oh, that was 1, 2, 3, 4, 5. Okay, I can count. So the open loop poles and zeros are 0.25 plus or minus 1.39. So here is 1.2, almost 0.4. Let's call it. There's where the open loop poles are. 1.4. So we can look at where the open loop poles and zeros are. We know that this is minus 0.25 minus 1.39J. This is plus 0.25 plus 1.39J. All right, so then what we're going to do is we're going to find out like where, oh, wait, we forgot the 0. We have to also put the 0 in. So the 0 is at, let's see, I better just do this math. 1/2 s plus 1 equals 0. 1/2 s equals -1. S equals -2. 1, 2. So here's where the 0 goes right here. So that's the 0. All right, so the first thing that we want to find out is where is the real axis segments. So we're going to start at plus infinity and walk back. 0 axis segments occur to the left of odd number of poles and zeros. 0, no, 0, no, 0, no, 1. Yes, okay. And that's it. There's no more of those. So we can pretty much tell you that the real axis segment goes here. How about asymptotes? So the asymptotes are the number of finite poles minus the number of finite zeros. That's going to be 2 finite poles minus 1 finite zero is going to be 1. There's a single asymptote. If you go through the formula, the asymptote is off at 180 degrees. So we've got the asymptotes. So here's the real axis segments. How about breakaway and break-in points? So one way that we can find out what the breakaway and break-in points are is that we're going to look at the characteristic equation. The characteristic equation is going to be 1 plus Kp GS equals 0. That's the characteristic equation. What we're going to do is we're just going to say then that Kp GH is equal to -1. That means Kp is equal to 1 over GH. There's a minus sign there. And what we're going to do is we'll just do 1 over GH. Is it okay? I'll just put the minus sign outside. This is s squared plus 1/2 s plus 2 divided by 1/2 s plus 1. So I'm going to call this f of s. This is some function of s. That's k. And what we'd really like to do, we'd like to find out what the partial derivative of k is with respect to s and set that equal to 0, because that gives us a max or a min, right? So we're going to do max or min that way. Oh, as an exercise to the student, you should go back and see if you could differentiate this and get a formal equation for this, but I'm not going to do it that way. I'm going to do it a little bit different way. I'm just down here in the corner somewhere. I'm going to do, so I cheated because I already know what the answer is here. 1, yeah, okay. So again, I'm just going to draw a little subsection. So this one is going to be f of s, and this one is going to be s, and then 1, this is -1, -2, -3, -4, -5. Okay, so that's when s is, and so really all I have to do is just plug this in and figure it out. And here's the easy way to plug this in is you just say, oh, you know what, I want s in MATLAB, I want s to be a vector from, let's say, -10 by increments of 1 to, by increments of -1 to 0. And then that'll set up the s vector. And then you can just, literally you can just plug it in to this equation here. It would be, f equals minus, begin parentheses, s squared plus 1/2 s plus 2. Adam has helped me with, he lent me some parentheses to put in here, divided by, begin parentheses, 1/2, I forgot the times, s plus 1, s, and this is going to give you some kind of, it says, I don't like the way you've done something. Well, you can't, s squared, so s is a vector, and if you do s squared, it'll come the wrong way, so you need a dot there. And if you divide one vector by another vector, you need a dot there. Those are to do element by element. That's to help you do element by element manipulations of each one of those things. And then, so I already did these what I get is at minus 3, I'm just going to see I can make this be however I want. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Minus 20 minus 10. See, right, I can, oh no, that's not S equals minus 10. This is F equals minus 10 right here. 1, 2, 3, 4, 5. This is minus 15. 1, 2, 3, 4, 5. Okay, 15. So it turns out that at 2, at S equals minus 2, something happens here. Look what happens when I put in S equals minus 2. S equals minus 2, that's minus 1 plus 1. Oh no, it's on the denominator. So at S equals minus 2, it's Buzz Lightyear. That's to infinity and beyond. All right, so that we don't even know where that one is. When I get to minus 3, so minus 3, it's down here somewhere. Minus 3, it is at 19. Minus 3, it's at 19 and change. Minus 4, it is at 16.667. 16, let's call it almost 15, 6. It's 16 and 2/3. At minus 4, it's a, oh, sorry, this is at minus 3.5. Oh, I forget it. I did this one too at minus 2. Minus 2.5, I think it may be minus 28. I'm just going to write that down and put a question mark by. I can't remember exactly the number. But at minus 3.5, it's 16.67. 16 and 2/3, 3.5 here. Minus 16.667. At minus 4, it is 16. Minus 16. At minus 4.5, it's also minus 16. And at minus 5, it is 16 minus 16.667. So you don't have to be like a freaking genius here to see that somewhere in between here, there's a maximum, right? And so that maximum is where it breaks away. So let's call that maximum breakaway point. I mean, so you could go through up here, make it go from here. Let's do it this way. We could do a new vector here that would be, let's say minus 5 by minus 0.01 to minus 4. We could do that vector and then still do the same F. And then that'll give us a more refined version of this. But for all intents and purposes, let's just call this a 4.25. Why not? Here, 1, 2, this is minus 2, 3, 4.24. Yeah, so this is 2, 3, 2, 5 is right here. So here's the breakaway points, right? It must be breakaway. They can't be break in. Oh, yeah, no, sorry, they are break-in points. Why was I saying breakaway? I don't know. I look, and I even have arrows. So this is where these two arrows break in. This is where it crashes in to the root locus. Now, what's important here is where do these roots break away? And I don't really know where they break away from, so I'm going to do a little bit of a test situation here. I'm going to choose, so I'm going to zoom in, really zoom in on this. Take a test spot that's really close to this pole. And then I'm just going to make it up. I'm just going to say, suppose I choose this is my value S. This is my value S. This is my test location. And what my objective is I'd like to know what angle does this vector from my point S to this root location, what angle does that make? I don't know. Because, see, that's going to make a difference. If it makes this angle that would be bad. If it makes this angle, that's one thing. If it, we don't know, but let's just go find out what angle does it make. And so what we're going to do is we're going to find out angle of departure from that spot. And what we're going to do for the angle of departure is we're going to draw, here, let's see, for the angle of departure, where am I going to put this? Angle of departure. Here, let's write that down here. Angle of departure. And so for the angle of departure, what we're going to do here is we're going to say Kp times GH equals -1. And so the angle of Kp times GH is equal to -180 plus or minus K360. So we can do it however much we want. And so what we have to do is we have to see what the angle, so K doesn't have any angle, right? So the angle of Kp GH, Kp is a scalar, so it doesn't have an angle. And the way it works, this is a minus the angle of S plus 0. Oh, minus the angle of S, whatever that, sorry, I did this wrong. It's minus the angle of S plus 2, only it's a plus, because zeros are on top of the GH, so they have positive angles. And then it's going to be minus the angle of S plus √1. And this is the angle of S plus √1. And I'm going to call that, and then it's going to be also minus the angle of S plus √2. And so this is √2 here. I'll just jot these in here. This is R2, R1. And now I'm going to find out what the angle of R2 is. So here is the angle. Oh, so really I should do it this way. I kind of did it wrong already. I should really do it this way, right? This is the angle. This is the vector S plus R2, not this one. But remember, this is infinitely close. And so what I'm going to say is that this angle, theta 2, equals 90 degrees. More or less, it does equal 90 degrees, right? And so now I'm going to find out what the angle to the 0 is. And it just so happens that I've done a good thing here. I drew the, if I draw a straight line from S, this is S plus 2. That's the vector S plus 2. And it just so happens I drew this. I didn't even mean to do it, but I drew this test point so it's in line. So whatever angle this is, let's call this theta 1. And then what I want to do is I'm always measuring my angles from, oh, let's call this theta Z, sorry. Not theta 1, theta Z, because this one I want to call theta 1. And so here's what we're going to do. So I'm going to, so now I'm having to, this is going to be plus theta 2. So, oops, I'll get up. I can, like, you can do the geometry if you want to. Do you like doing geometry? I don't know. If you like doing geometry, go ahead and do it. But I'm going to do this one. I'm going to call that, 37 degrees. And then S plus R1, I don't know what that one is, minus theta 1 minus 90. See, that's 37 minus theta 1 minus 90. That tells me, this is telling me that theta 2 is equal to 127 degrees. And then all I have to do is up here, I have to just see which way does theta 2 really leave. So here's 100, 20, 127 degrees. I'll just draw this in like that. So we know where it goes. This is 127 degrees. Theta 2, theta 1 equals 127 degrees. Sorry, I have all my subscripts messed up here. because I did them a different way on mine. So 127 degrees, I can just draw that in just like this, right? So I know that the angle of departure looks like that. So now I know what the angle of departure looks like for both of them, the 127 degrees, right? So I can assume that these things like come in here and crash in somewhere like that. And now I'm going to get my compass out. I had a student come back from Germany. And I'm going to show you something. There's a thing with, I think it's with second order systems, there's a whole math thing we can delve into if we want to, but I prefer not to delve into it if I can help it. But I'm just going to show you that it turns out that there's a rather specific shape that you can make here. So I'm going to cheat just a little bit. I'm going to get all my stuff lined up just right. Right? So you see what just happened there is that this guy is a circle. It's a perfect circle. So the way this thing works is that this just goes in. Boom. This one goes around this way. Boom. You can just sketch it in, but I happen to know that you can prove mathematically that this is a circle around the zero. If you have two poles and you have a zero, it's a circle. Too bad. And we pretty much kind of figured that out. So this curve that I have here represents any place in the S-plane where I can put the roots of the characteristic equation using this control structure, which is Kp. I can use it any way, any place I can do it. And, again, I can choose many different things, but why not just choose zeta equals 0.707? That's going to be right along the 45 degree line right here, right? So let me put a dashed line there. So I'm going to choose, I don't think I did that right. Oh well, you get the idea. I'm going to choose this and this to be my desired root locations. So those are my desired root locations. Okay. So let's see. Now, all I have to do now is I have to figure out so all I know is if I make this gain bigger or smaller, I can make it go on to those root locations. And so now what I'm going to do is I'm going to find out what the gain is. Sorry, my green pen isn't working. Must not be the same green pen I was using earlier somehow. All right. This one's not working very well either. Find Kp. Let's find Kp. So here's how we're going to find Kp. We're going to use the magnitude. So this is the angle criteria. I should write this down here. Angle criterion. And this one is going to be the magnitude criterion. Right, we're going to find Kp. And what we do with this one is we say 1 plus Kgh equals 0. Kgh equals minus 1. The magnitude of Kp, I'm going to put p's there, Kp times the magnitude of Gh equals 1. And that means that Kp is equal to 1 over the magnitude of Gh. And the magnitude of GH is easy enough to do because what I'm going to do, this is S plus R1, S plus R2, right? And I have it in the right form, S squared. If I had a leading coefficient here, I'd want to divide through by that leading coefficient so that I can write this vector, S plus R1, and this vector, S plus R2. Now you'll notice here, I do not have a leading coefficient. And so I'm going to change that. This is, so let's see. I almost did this at 1/2 S plus 1. So let me write this a different way. I'm going to write the s plus 2 equal 1/2 times s plus 2 equals 1/2 s plus 1. So I'm just going to change that so it does have a leading coefficient. So I'm going to put that down on the bottom here. This is a 1/2 s plus 1, right? That is, and technically speaking, I want to put the magnitude of these things. And do I need a magnitudometer? Yes, I should get a magnitudometer. So let me just draw those vectors in first. So let's see, s plus r1. What is the vector s plus r1? Well, here is the root 1. So I'm going to draw this vector in. This is s plus r1. And then I'm going to draw the vector s plus r2. Here's s plus r2. Vector s plus r2. And then here's a vector s plus 1. That's the vector to the 0. I'm going to draw that one in too. And here I'm going to s plus r2, s plus 0. Those are those vectors. And so now I'm just going to measure them. Let's measure this one first, right? Sorry if I'm going to do this. You know, how accurate does it need to be? I don't know how accurate it needs to be. Let's call that, let's call that one 2. S plus R1 is 2. Okay, let's measure the 0. Distance to the 0 because it's almost the same. Okay, let's call that one. Let's see, this is 2.2, the 2.3. Right? And now let's measure the length of the vector s plus r2. .1. I did the last time I measured it was 4.05. Is it okay if I just write 4.05? Just because I've already done the math for that. Oh, it doesn't really make any difference. 7. Kp is equal to 7. And so if I do that, I'm going to get exactly the right thing on my root locus. Yeah, I'll scan this and give it to you. All right, then, let's go on. So without doing your homework assignment for you, let's go ahead and let's look at a different problem. Let's look at, in the exam, problem 4. Now, problem 4 is going to be good because it's going to give us a couple of different options here. So one of the things that we know in problem 4, here's what it looks like. 1 over s plus 5. There's a disturbance in here. In the end, we probably want to make sure that our disturbance rejection is okay too, right? So that's something that we'll probably want to take care of. And then here, this one has just another gain that's got something like a 20 in there or something. And so again, if we were, going to be making a control system here, we're going to put a controller. This time I'm going to leave it a little bit more vague here. I'm just going to say this is the controller. The controllers, we always want to find the error. I'm going to do this too because I still want to emphasize that what we're looking at the open loop system. So before we do the open loop system, let's just go ahead and do, okay, let's see. I'm going to put my, I'm going to put my desired root locations, roots. Let me talk about that in a minute. I'm trying to plan ahead enough to be able to put this stuff in the right spot. So We'll try and use up as much of our graph paper as we can. So here's this. We're going to put this guy going across this way. I don't know what we're going to run into. Let's see. I'm going to do it this way. 1, 2, 3, 4, 5. Yeah, okay. Minus 5. 1, 2, 3, 4, 5. Minus 10. 1, 2, 3, 4, 5. Minus 15. Oh, I probably could have made my scale different, right? Oh, well, good, because I didn't do it right. Oops. Okay, well, let's just do it right. 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is minus 10. Oh, yeah, that's how I wanted to do it anyway. This is 11, 12, 13, 14, 15, minus 15. Yeah, let's try that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's try that. 1, 2, 3, 4, 5. 1, 2, 3, 4. Uh-oh, this is only 9. So I might change where my desired root locations are. It doesn't really matter where they are. I'll show you. See, I might have to get a bigger piece of paper or something, right? So the first thing to do, let's just first, for the heck of it, let's draw the root locations for the open loop system without a controller. So if all we do is put a proportional gain on it, the first thing we could check is to see what the dynamics of the open loop system are. And are those sufficient? Then we can just tell it 5, put an input of 5, and it'll go there. But in this case, that's not sufficient. So this has got a root at s equals 0. And this has got a root at s equals 5. Minus 5. And then again, we've done this enough times that we don't really have to mess with it too much. I'm gonna get something. This is gonna be, I'm just gonna real axis segments. This is 1, 2.5, and this is gonna be, we did this one, so this is where it goes. We did this once upon a time, and what we found is that as, so for instance, we might choose a 45-degree angle here. I should just be able to just do 45 degrees by looking at the corners of my thing here. We could just choose a 45-degree angle here if nobody has any other specifications, and we say, okay, well, that's the gain that we need to use. And you can use the magnitude criteria now to find out what the gain is if you want to. But we can also see that this is minus zeta omega n is equal to 2.5. That means the settling time is going to be 4 over zeta omega n, and that's going to be 4 over 2.5. That's about 2 seconds, right? So you're going to wait 2 seconds for this thing to settle. Is that fast enough for you? Well, not if you're in a Boeing 737 MAX and you're heading to the ground, baby. You want more speed than that. So let's say for the Boeing 747 MAX, let's put them at 10. Let's make it plus or minus 8 because I messed up and didn't make my thing big enough. So here's my desired root locations. Minus 10 plus or minus 8j. You can go figure out what this is a little bit. So you can see it's a little bit under the 45-degree line, so it means it's a little bit more damped than 45 degrees. Perhaps that's not a bad thing to worry about on your aircraft if you have your desired root locations. Did I do that right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I didn't put that in the right place. I thought that looked a little skewed. Okay, sorry. All right, so, what's the difference between this one and the last one we just did? Oh, it's got a 0 there. It's got a 0. Can we just add a 0? Why not? Here, I'll do this one in I wish I had a better green pen. Is this a better green pen? Oh, good, this one is. Okay, let's try this one. Let's add a 0 at s equals minus 10. Well, we don't even know what that looks like. So what that means is this is gonna. I'd like to draw it in here, but I'm gonna draw this over here. Controller 1 Kp times s plus 10, right? I don't know. Just put it in there. We're just doing stuff, and we'll find out what that means later. But let's just put 1 in. Kp times s plus 10. Now we have a 0 in here. Okay, so one of the things that we could do is if we're looking for the angle of arrival, do we need the angle of arrival? Sure, let's do it this way. We're going to do that K1 plus Kp GH. I'm going to kind of put GH in parentheses here is equal to 0. That means Kp times GH is equal to minus 1. That means that Kp is equal to minus 1 over GH. And why do I have this in parentheses? Is because I'm going to include, so what's on top is the 20. That goes on the bottom now. I'm going to include this s plus 10, right? That's why I have it in quotes. I'll put that in quotes. And then over here I have s plus 0, and I have s plus 5. So that's what my Kp value is, and I'm going to call that as f of s, right? So I can go through and find out what f of s is. Okay, so if you go back over and look at the last problem, this is going to tell me that the f of s, so when I do the derivative of Kp with respect to s is equal to 0, or I can just plot this and look for, I can just either just plot here, this is f of s, and this is s, and then this is Kp here, and I just look for this value, the maximum value, and it turns out that maximum value is 17.05. If we try it out, 15, 16, 17. So that's where the angle of arrival gets to be, right? Because one of the things that happened here is if we look at where the real axis segments are, this adds another piece of real axis segment here. What we used to have was the number of finite poles minus the number of finite zeros, which is 2. So there were 2 infinite asymptotes. When we add a 0, there's only 1 now, and it's at 180 degrees, so it looks something like that. And I think I kind of told you something about things being circles. Yeah, there's some kind of rule about that somehow. Oh, I probably chose my. I think it goes like this. All right, so that one, it doesn't quite go through, right? It doesn't quite go through the point that I'm interested in. And so what I could do is I'm just going to use the angle. I'm going to use the angle criteria. Angle criterion, and I'm going to say that the angle of K, P, G, H, I'll use that still, has got to be, it's going to be minus the angle of S plus, or plus the angle of S plus 10, or S plus, let's call that alpha, because we don't know what it is, right? We need to find out what alpha is. It's going to be minus the angle of S plus 0 minus the angle of S plus 5, has to equal minus 180 plus or minus K360. All right, so let's see what that's going to be. So we don't know that one, but we know what that one is. Here, let me draw it. Oh, geez. Okay, let me draw it. What happened to my ruler here? Okay, so let's do it. I'm going to do it in red so we can see the difference. There's that one. There's that one, right? So this is going to get a little messy, but you know, you have to do your own. You should be following this along anyway. If you don't have a protractor, they sell them at, I think they used to sell them at the drugstore, but I don't know if they do or not anymore. So let's call this is 140 degrees. Can we call that 140 degrees? 140. Let's see what this one is. This is 120 degrees. 120. Right? And so now what we can do is, so this is a minus 140 minus 120 equals, and this is the angle of alpha is equal to minus 180. I always get the minus signs mixed up here. So let's see, we're going to add 120 and add 140 to get 40, 50, 60. This is 260 minus 180. 10, 16 minus 8 is 8. I have to borrow one. So that's 80 degrees. Oh, alpha equals 80 degrees. So let's see, what is alpha here? Well, it's not that. If it was 90 degrees, that'd be perfect, right? But if it's 80 degrees, it's something else. And so I'm just gonna draw this here. I'm gonna draw it in the right spot, and then I'll give you my. See, this is 80 degrees, and I'll show you why I can just do it that way. Because guess what? If this is 80 degrees, then this is 80 degrees, right? So I can just draw it right there. And what this tells me is that where I really need my 0 is not here at 10. Where I really need my 0 is right here. That's at 10, 11.5. That's where I need my 0. And when I do my 0 at 11.5, I'm just going to show you what happens here. Again, what you can show is when I do my 0 at 11.5, that is what happens. So that's my new root locus. And I'll just see if I can get a green one and draw this root locus in. So I'll just draw it like this. Boom! Goes right through that spot, right? Isn't that beautiful? And this one goes this way. Here's the other root locus branch. A lot of times you don't even need to do the minus side of it. That goes through the plus, right? And so all we have to do is find out what the gain for that value is. So that's what happens if we added a 0. But guess what? In real life, you can't add a 0. In real life, you have to add a 0 and a pole. We'll discuss it more. It's causal. So let's call this S plus A, that's the 0, and S plus B, that's the pole. And this is called a lead controller. Now, what changes on a lead controller? The only thing that changes on a lead controller is that when we do the design for the lead controller, we're going to do that a little bit differently. It's going to be the angle of KP times GH has got to be equal to plus the angle of S plus A minus the angle of S plus B minus the angle of S plus 0 minus the angle of S plus 5. Right? So those are the angles that we need. And since we have those already, this is going to be one. This is 140. This is 120. This is 80. But what we don't, we don't know 80 anymore. We don't know this one. But what we know is 120, we know 100. So the spot that it has to do, we have to get it to, it goes like this. So this is S plus 0 is minus 140. S plus 5 is minus 120. That's minus 260. And so let's look at what angle of S. So where is B? Well, what we want to do is we want to put B out here someplace. Minus B. And then what I'm going to do is I'm going to draw, this is the angle of S plus A. And this is the angle, this is the vector S plus B. So here's the angle, this is S plus A. I'm keeping it, it's not 80 degrees anymore because I don't know where it is. It's just general. And here's the angle S plus B. So if this is the angle of S plus A and that's the angle of S plus B, then this is the angle, here I'm going to do it in a different color here. This is the angle S plus A, and this is the angle S plus B. So guess what this angle is right here? This is the angle theta A minus theta B. So what I know in my equation down here, the angle of KPGH is equal to the angle of theta A minus theta B minus 140 minus 120, and that has to equal minus 180 plus or minus K360. And you know what I already figured out? I already figured out that that angle, A minus B, has to be 80 degrees. So I'm going to get a piece of paper here, and I'm going to mark, here's my 0 spot right here, and I'm going to mark 80 degrees, 20, 34, oh, well, I'm going to have to do it off here. So here's 80 degrees. From here along here, this is 80 degrees. So that means that what I'll do, now I get to use the pin on my protractor for yet another noble cause. Look, I'm going to pin that down. This angle, anywhere, I put this angle anywhere I want. And look, if I put the 0 at infinity, it's 80 degrees. Can you put a 0 at infinity? Yeah, come on, we know enough about infinity to say probably not. So let's put it somewhere else. How about 10? I could go off and measure where that vector crosses the origin. I could keep going. It's better to keep these things out as far as you possibly can. Oh, what if I do that? Oh, let's try that one. Let's put the 0. This is kind of cheating. It's not a good way to do it, but why not? Let's put the 0 at S equals 5, and then that makes us have to put the pole then. So 17, 18, 19, 20, 20.5. And so now what we've done is we've designed our controller where A equals minus 5 and B is minus 20.5. And if we design our controller, our lead controller, it forces the root locus to go exactly and precisely through our desired root locations in the S-plane. Perfect. And we're done. So we're going to have to want to simulate all this as well, right? And I'm also going to tell you, it's not a bad thing to try and cancel poles and zeros. I mean, we'll talk more about this. In general, you don't want to. In general, what you want is you want to push this pole out as far as you can get it out there. You know, if you can get it 3 or 4 times out farther than your dominant root locations, you're good. And then wherever this one goes, you just have to live with that. Okay, so you can try those things. All right. Hopefully this will help you and at least give you some questions to ask when you come to class.